Hello, my name is Hannah, and this is my presentation on my landing gear control system prototype and quality assurance evidence. The presentation demonstrates a simulation-driven landing gear control system prototype developed in C#. As you can see, I have the 3 or 4 C# pages. The aim of this work is to model safety-critical behavior using state-based logic, integrate configurable parameters and sensor inputs, and apply quality assurance techniques to validate and improve system behavior. The prototype was developed as a simulation-driven system and designed around an explicit finite state machine. System behavior is represented from a small set of clearly defined operational sets: down, moving up, moving down, and fault. Guarded transitions are used to prevent unsafe operations such as retracting on the ground or extending above allowable airspeed. The system initializes in a safe default state to minimize risk at startup, and logged output is used throughout to provide visibility of system behavior during execution and testing. A PDCA approach was followed by first verifying baseline behavior and then introducing single safety improvement and revalidating the system to ensure existing behavior was preserved. This component diagram illustrates how the logic, configuration handling, sensor inputs, and validation outputs are integrated within the prototype. This component acts as a test interface. It allows manual simulation of pilot commands and sensor inputs without requiring external systems. Commands are passed directly into the controller, allowing the behavior to be exercised in a controlled and repeatable way. The gear controller contains the core control logic. It manages the current system state, evaluates guard conditions, and determines whether commands are permitted, inhibited, or result in a fault. Sensor data represents simulated aircraft inputs, such as weight on wheels, which is WOW in my presentation, airspeed, which directly influences allowed state transitions. Configuration values are stored separately to allow safety thresholds such as speed limits to be adjusted without modifying the control logic. The configuration loader reads these values from a JSON file at runtime, supporting configuration control and flexibility. Log output provides observability of system behavior, allowing decisions made by the controller to be verified during testing. The state machine represents the states by which the system is in. Down represents the safe ground state and the system's default initial state. This transition is guarded to ensure retraction only occurs when the aircraft is airborne and above minimum airspeed. Moving up represents the intermediate transition state, while the gear is retracting. Up indicates that the landing gear is fully retracted and locked. Extension is permitted only when the airspeed is below the configured maximum extension speed, and moving down represents the transition phase while the gear is extended. Down here we have the fault state, which isolates unsafe or invalid conditions and prevents further operation until a reset is performed. Fault transitions can occur from any operational state, ensuring unsafe conditions are handled immediately. Before introducing any improvement, baseline behavior was verified using command line test harness. Test cases were derived directly from the state machine and focused on safety critical scenarios such as blocked commands, invalid operating conditions, fault handling, inputting data wrong. Expected data was compared against the actual behavior using logged output and execution evidence as captured via screenshots. For example, this test confirms that the extension is correctly inhibited when airspeed exceeds the configured limit. And the example here is the figure A1 confirms that the extension was correctly inhibited when airspeed exceeded the configured limit. As you can see, it says retract blocked aircraft on ground. This is a test execution flow diagram. Each test begins with a controlled setup where the sensor values and configuration parameters are defined. A command is issued via the CLI test harness, and the controller evaluates guard conditions to determine whether the command is safe. Based on this evaluation, the system either transitions state, inhibits the command, or enters into false state, which we could see from figure A1. Logged output is used to verify that observed behavior and make sure that it matches the expected results. A root cause analysis was applied to identify some potential safety gaps. For example, an inconsistent sensor inputs were identified as a potential hazard, as they could potentially lead to ambiguous behavior if not explicitly handled in real practice. As a corrective action, continuous fault monitoring was introduced. Prior to the introduction of sensor disagreement detection, the baseline prototype did not explicitly handle inconsistent sensor inputs and would remain in its current operational state. Following a controlled change, the system now transitions immediately into a fault state when implausible sensor combinations are detected. This change improves overall system safety whilst preserving previously verified baseline behavior. In fact, I can probably even show you this in real time. The core control logic is basically implemented in the gear controller. A single state variable represents the current system state and initializes as a safe default. Commands extend and retract. Commands such as extend and retract, let me find those. So it's extend async and retract are guarded using sensor and configuration checks, ensuring safe commands are inhibited rather than executed. Fault monitoring remains during the update cycle, and when an implausible sensor condition is detected, the system transitions into the fault state and logs the reason. Appendix A shows the system entering the fault state due to a sensor disagreement, confirming that the controlled state change behaves as expected. Safety was enforced through guarded transitions, ensuring unsafe commands are blocked before any state change occurs. Faults contained within a dedicated fault state prevent unsafe behavior from continuing. Establishing verified baselines ensured that improvements could be evaluated objectively and prevented unintended changes to existing correct behavior. Logged output provides traceability for all system decisions, including testing. The prototype demonstrates how state-based control logic and quality assurance techniques can be applied to a safety-critical system at a conceptual level. Establishing verified baselines was essential to ensure improvements enhanced safety without introducing regressions. With additional development time, the system could be extended with actuator feedback sensors, timeout and escalation logic, fault escalation logic, and automated test execution to further improve realism and traceability. Overall, the work demonstrates a controlled, safety-focused approach on the prototype development, validation, and quality assurance. I didn't create a crazy amount of components because I just wanted to focus on quality assurance and making sure that the prototype development and included a lot of validation and everything was robust in increments so I could easily trace where I'd made mistakes or where the system maybe had a fault, because in safety critical systems and in safety critical software, this is imperative. Thank you so much for listening, and please let me know if you need anything else from me, whether it be documents or code snippets or even a zipped file of the code.